So guys, unbelievable but true. This is it. This is the last of the anything that you're going to learn this year. It's crazy. I can only take your applause in its best potential way of understanding it. That's right. It was meant to be. That's right. So guys, the other thing about today is so fast. Not maybe 10 minutes, 15, maybe. It goes really, really quickly. So all of that then to say, guys, this is the topic for your notes today. The same guy that came up with the number, Avogadro. We didn't really talk about this, but actually when Avogadro proposed that number and even the concept of the mole, he was actually studying gases. And so this is all interrelated. And then he came up with an idea called the ideal gas law. And so we're going to do that today. We're going to talk about it conceptually, then we're going to talk about it mathematically, then we're going to solve two problems, and then we're going to be done. Now guys, let me tell you right up front, you're going to walk out of here going, I understand the Avogadro's principle. And you will, because I like the way I teach this. It's kind of inventive. So you're going to understand Avogadro's principle until you all come back for AP next year, well, the ones of you that are, and then all of a sudden you're going to go, man, I thought I understood that, but in fact, I guess I really don't. So understand, guys, that we're going to do this real superficially today, and then we're going to dig a ton deeper when we get into this next year. So guys, with that said, we are going to do some visual stuff today, and because you guys are smarter than the average gathering of students, let's just let the cat out of the bag right now. This is actually not hydrogen gas. How do you know that? Because it floats. And this is not butane, because that's the stuff inside of a Bic lighter, and if it were to pop, it could explode. So guys, we are going to use these as fictitious samples of gases, but rather than allow one of you to go, wait, that's not really the gas, well, let's just talk about it right now. I blew these up about 20 minutes ago, but we're going to pretend that they are. So guys, you ready? Avogadro's principle in a nutshell. Don't write down this first page of stuff, but I need to develop a misconception so that we can then talk about a correct conception. And to do that, I need a trash can that's not full of pizza boxes. So we're going to move this over here, and here we go. Okay, so guys, this is about a 30-liter can. I can't believe I'm touching this without gloves, but guys, 30-liter trash can, okay? Now, it doesn't really matter the volume, although we are going to talk about volumes today. But guys, we are going to develop an important scientific principle. You ready? So imagine, and it's actually 30-gallon, it's not 30-liter. So we've got a 30-gallon trash can up here. And guys, here's the thing that I want you to estimate. How many of each of these things would be required to fill the trash can? So first of all, tennis balls. If we were to try to fill this trash can with tennis balls, how many would it take? So something about that big, right? 80, 100, 120, 150. Let's just use a round number and let's say 100. So guys, 100 tennis balls. This is the point where we need to actually draw the distinction. What if we used volleyballs? If we were to fill this thing with volleyballs, how many volleyballs would it take to fill the same trash can if we emptied all the tennis balls out first? 7, 8, 9, maybe. Let's go 10 because that's another even sort of number. So guys, we understand a very important principle, and it's so very obvious that you all understand it, but let's actually put it in writing. So guys, would you agree with this hypothesis that it takes more small things to fill a volume than it does big things? Doesn't that make sense? So we said about 100 tennis balls, about 10 volleyballs, because the tennis balls are smaller than the volleyballs, therefore it takes more of them to fill the space. You get the idea? Okay. Now guys, with that as our hypothesis, Now let's have that same conversation based upon these two balloons. And again, guys, you know that they're really not these gases because, frankly, I don't have pure samples of each. But guys, let's pretend as if they were. So guys, it goes like this. The blue balloon, did you notice the tiger colors? Blue and gold, yeah. All right. So guys, and again, we're pretending like these are these gases. So guys, the blue balloon, the one on your right, we are saying, get back here, we are saying is full of diatomic hydrogen, okay? Little itty bitty H2 molecules. Now guys, this balloon, and we really could do this. We could gather these gases together. This balloon is full of these, which are butane molecules. Okay, so the one on the right, itty bitty hydrogens. The one on the left, big old butane molecules. Now you ready? The same question stands. Guys, which balloon contains more molecules? The one that's full of the bitty hydrogens or the one that's full of the big old butanes? Which balloon contains more molecules? Hydrogen, right? Why would that be true? Because the hydrogen molecules are smaller. You get the idea? Guess what? Completely wrong. Guys, this is the surprising answer to the question. If these two balloons were in fact full of hydrogen and this one full of butane, they would contain exactly the same number of molecules. There would be exactly the same number of molecules of hydrogen in this one as there are butane molecules in this one. And now you're saying, wait a minute, I thought I understood the trash can. I thought I understood our hypothesis. I thought I understood that it takes more small things like tennis balls than it does big things like volleyballs to fill a volume. And now you're telling me there's exactly the same number of these small guys in here as there are big guys in here. How can that be? Go ahead, Tyler. Kind of. It'll get there in a minute, but not quite. Guys, where is the logic breaking down? And guys, understand, everything that I've told you is true. It's not like I'm going to come back and go, psych, that's not really the case. It does take more tennis balls than volleyballs to fill the trash can, and there are exactly the same number of hydrogens as butanes. Why doesn't our model fit in both instances? Jared? Exactly. Yeah, guys, let me show you the difference. Here's the problem. This is your mistaken idea of what gases look like. So guys, these are airsoft BBs. We're going to let them represent the hydrogen molecules, and these are obviously ping pong balls, and we're going to let them represent the bigger, and the ratio is pretty close, the bigger butane molecules. And guys, if this is what gas molecules did, there would be more hydrogens than there are butane molecules. But guys, this is not how gases behave inside of balloons. Jared, what are they doing? They're moving around at hundreds of miles an hour. So guys, this is actually what the model looks like. These spaces are not completely full of the gas molecules, right? They're not laying on each other like tennis balls or volleyballs in a trash can. It's more like this. There are just a couple hydrogens, there are just a couple butanes, and they're moving around at hundreds of miles an hour, and it doesn't really matter if they're small like hydrogen or big like butane. There's so much empty space around them that the small difference in the sizes of the molecules themselves doesn't matter. And so if the beakers or the balloons have the same size, there will be exactly the same number of particles because the empty space is so much bigger than the size of the molecules themselves. Getting back, Tyler, to what you said. Go ahead. It does, but it's not because of their size, it's because of their mass. Yeah, we'll actually talk about that a lot in AP. And size and mass are related, right? And so it does in fact turn out that these things are actually moving faster than these things, and you can actually figure out their masses, their sizes, depending on how fast they're moving, because if they're at the same temperatures, the small guys will move faster than the big guys. We talk about that a lot next year. Yeah, go ahead. And that's exactly the application of this, because it doesn't matter what kind of gas, right? It could be hydrogen, it could be butane, it doesn't matter. 1 mole of gas has a volume of 22.4 liters, and it doesn't matter what kind of gas it is, because in fact, when the balloons or when the molecules fill the space, it's not like they're all packed together like this, it's that they're all moving around, and as a result, they all have the same molar volume. Do you guys get the idea? Okay, so guys, we're going to leave it at that. That's Avogadro's principle. We are almost done for the day. We will make this way more confusing next year, but for now, let's put it in writing. You ready, guys? This is the stuff you need to get in your notes. So, in a nutshell, Avogadro's principle says this: 2 similar gas samples will contain the same number of molecules because the particles are not in contact, but they're small, rapidly moving objects, which is exactly what Jared and Tyler and some of the rest of you contributed. That's exactly the idea. Yeah, exactly. You'll notice that I underlined and italicized it. We're going to talk about, here, let me just bring it in. We're going to talk about that right now. So what does it mean that they're similar? And I'm not going to tell you, I'm going to ask you, and you'll come up with them. Let's do it. Well, here, let's let people finish writing, and then we'll talk. And Tyler, you just got 2 of the 3. Do you guys like the airsoft analogy? It's pretty good. Came up with that myself. I should be a teacher. I think so, right? Well, no. 24 years later, I can tell you, no, I shouldn't say that. The fact that I'm still here tells you that I still love it. Although a couple years ago, I was pulling my resume together. I was ready to leave and get into medicine. And then I talked to my brother, who's a neurologist and hates it, and I decided to stay, and I'm glad I did. You guys okay? You caught up with me? All right, so guys, you're right on it, Emily. What on earth does it mean when we say similar? Now, guys, you got to give me the benefit of the doubt here. I promise you, when I blew these up right before lunch, they were the same size. This one leaks, apparently. So let's talk. So, guys, what we're saying is this. These 2 gas samples, again, we're pretending hydrogen and butane, right? Guys, these 2 balloons contain exactly the same number of molecules. But in order for that to be true, how are they similar? So what do these 2 samples of gas have in common? They have the same size. Can we call that volume? They have the same pressure. And how do you know? Because they're both being exposed, and good for you, Emily, used exactly the right term. They're in the same atmosphere. So they have the same pressure pushing on them. And what else do they have in common? Same temperature, because they're in the same room. So guys, those are the 3 things that have to be similar. Same pressure, same temperature, same volume. So guys, if they have the same temperature, the same pressure, and the same volume, they will have the same number of molecules. And again, guys, as Avogadro was developing this idea, that's where he started thinking about counting molecules, which ended up with the idea of the mole. So there you have it. You guys okay with the idea? You're good? All right. So guys, if you understand Avogadro's principle, we now need to talk about what is called the ideal gas equation. So guys, the ideal gas equation simply does this. You ready? Look at the variables. We have volume, we have temperature, we have pressure, and we have numbers of molecules. But guys, how do we count numbers of molecules? In what units? Moles. And the ideal gas equation brings these 4 variables together, and it does it like this. It is the Pivnert equation. You will actually hear this called Pivnert. Now guys, again, the idea is we've got pressure, we've got volume, we've got N, which is number of moles, T, which is temperature, and it establishes a relationship between them. So let's define our variables. P, of course, is in pressure, and that's got to be in kilopascals. V, of course, is volume, and that has got to be in liters. N, and this is a new variable for you, is numbers of moles measured in moles. Now guys, R is a funny one. R is actually what is called the universal gas constant. So guys, here's what happened. As Avogadro was studying gases, the equation was originally PV equals NT. And he started plugging values into this from his experiments, and he found out that PV does not equal NT. But PV was always 8.31 times bigger than NT, and so he put in a fudge factor, a constant called R, which then became the universal gas constant. So R, which has a value of 8.31, is actually the number that is required to make PV equal to NT. And you'll notice the units, liters, kilopascals over moles Kelvin, are actually the units necessary to make everything cancel out. And then T is temperature in Kelvin. Now guys, understand you won't have to memorize any of that. It will be on the test that you will be taking on that fateful day 2 weeks from now. Next, not this Wednesday, but next, the 27th, I guess. But remember, you'll actually be taking it during second period. And that will be your very last class of the year. No, so our finals week goes Friday, B1, B2, B3 done at noon. Tuesday, A1, A2, A3 done at noon. Wednesday, B4, A4 done at 10:20, whatever. So, and then yearbooks, yeah.
So you said this is our last Monday?
Yeah.
What are we going to do?
So what's going to happen is Friday we're doing a lab where you will actually measure R. And then Tuesday, we're going to check in lab drawers and turn books back in. And then Thursday, we'll review for the test.
And our final is just on this.
Your final is just the unit test. Yep. Okay, so guys, here's what we're going to do with this. You now understand there's a relationship called Pivner. You now understand there are variables, and you are going to be given 3 of these 4 variables, because R is not a variable. It's 8.31. You're going to be given 3 of the 4 of these, and you've got to solve for the other guy. So we're going to do 2, and then you'll work on your homework. So guys, here we go. Number 1, it says this. Write it down, and we'll solve it together. So again, you're going to be given 3 of the 4 variables. You've got P, V, N, and T. R is 8.31. And guys, all you've got to do is write down the equation, plug in the information that you're given, solve for what you're not. So guys, if you read the question, you'll notice that you're given numbers of moles, and then you're also given temperature and pressure as being standard. You don't have to memorize them. I will give them to you on the test. So again, guys, the question says, what is the volume of 1.00 moles of methane, CH4, at standard temperature and pressure? So guys, give yourself every advantage to get this right and write down the equation first. Then, guys, what we're going to do is we are simply going to start on the left. Grab your calculators, you'll need them. Start on the left and work to the right. Allow the equation to drive the process. So we need P, we need V, we need N, we need T, we already know R. So guys, what pressure are we given in this problem? Standard pressure, you don't have to memorize it. It's 101.3 kilopascals. Again, standard pressure, it'll be on the test. Then guys, volume, the first 2 words say what volume? So that would be our X. Then guys, N, this is our new variable. N is moles, 1.00 moles. Then guys, by the way, for R, it's 8.31. If you don't put units on it, you're okay. You can just put 8.31. And then, guys, standard temperature is 273 Kelvin, which is 0 Celsius, like so. Then again, guys, just like all these other types of problems, I'd really rather not see your math. We've got 4 significant digits, 3, 3, and 3 significant digits. So you go through and do the math. 1 times 8.31 times 273 divided by 101.3. And oh my goodness, what answer do you get doing the math? 22.4 liters. Wait, that sounds familiar. So you're telling me that the volume of 1 mole of gas is 22.4 liters? Guys, you've known that since January. Did you kind of notice, though, the way I talked you through this problem where I didn't make eye contact with anybody and I raced you right through it? The reason is because I knew if I dwelled on this long enough, one of you would go, isn't it 22.4? Because you've known all along that the volume of a mole of gas is 22.4 liters per mole. So 1 mole of gas, add STP, takes up a volume of 22.4 liters. You've known that. Now you know where that number comes from. Get the idea? All right. So would any of you come up with that? Jay already mentioned it a while ago where he's talked about. Would you? No? All right. Anyway, you okay with the math? Guys, we're going to do one more and let's get you going on homework. This one's a little trickier. It says this. A small rigid container, that sounds official, holds 250 milliliters of helium gas at room temperature and a pressure of 85 kilopascals. What is the mass of the gas? So I'll let you catch up and then we'll talk about how to solve this. Oh, man down. You guys all caught up? You okay? Not quite yet? So guys, let's take a swing at this. If you read the last sentence, what are we solving for? What is the mass? Now guys, if you throw PivNerd on your paper, you'll immediately notice that you got a problem. Because your goal is mass, and there ain't no mass in PivNerd. So what are you going to do? Well, which one of these variables, if we were to solve it, could we convert it into mass? Moles, right. So what we're actually doing is solving for moles, and then we can convert one-step dimensional analysis into mass. So we're solving for moles, which means we need a pressure, which in this problem is 85 kilopascals. Now we need a volume. Please do not write down 250 milliliters. Why not? It's got to be in liters. And how do we convert? Divide by 1,000. So it's 0.25 and then conserving significant digits, 0.0 liters. Then guys, are we all okay with the idea that our variable that we're solving for is moles? And then we'll convert that into mass. So that's our X. Then guys, again, you don't have to memorize R. It's 8.31. You also don't have to put units on it. And then guys, our temperature is not 22 degrees Celsius. Add 273 and it's 295 Kelvin. So guys, again, I'd really rather not see your work on this, but if you want to talk through it, you're going to go 85 times 0.25 and then divide that by 8.31 and divide that by 295. And guys, I'll be honest with you, I'm not real, I did this hurriedly during third period. Can you verify 0.0087? Is that correct? Oh, good. Okay. Yeah. technically you're right. We should, because it's an intermediate calculation. If you do, it's not wrong. And technically, Carson, yes, we should, but I didn't. But yes. Did you guys hear what he said? Shouldn't we include an extra significant digit because it's an intermediate calculation? The answer is absolutely. Go ahead, Jay. Well, it does, and here's why. So we're not done, right? Because we're solving for mass. So now what we need to do is we need to bring this number of moles down, and we need to convert it to mass, right? And so in order to convert from moles to grams, we need to know the molar mass. So 1 mole of helium has a mass of 4 grams. And then when you do that math, I get 0.035 grams. So the bottom line here, Jay, is this. It doesn't matter what the gas is when we figure out how many moles. That's Avogadro's principle. But then when we figure out the mass, it does matter because each different gas has a different molecular mass. So guys, that's it. Good night. You've got 50 minutes to get your homework done. I know this is a little bit of a letdown that on the last day of class you won't have homework, but I suspect that your homework just became classwork because you really should get this done in the next 50 minutes. I'll put the answers on the wall. Why don't we get this assignment done? When I see you Friday, we'll do a lab. And guys, don't forget on Friday, your absolute 0 labs are due. So if you would like, I can get rulers and more graph paper, and you can work on those as well today. So guys, you got lots to do. Let's keep busy. Go get them.